Welcome to this session, Protecting Your Data with SQL Ledger. My name is Dennis Torres, so I'll be talking about this new feature called SQL Ledger, which is available in SQL Server 2022 and Azure SQL. My demonstrations today will be on Azure SQL, but there are only a few differences when working with SQL Server 2022. So, this is me. I'm a data platform MVP. Work at the Tower Software in Malta. I'm the Malta Data Platform User Group Leader. I'm a trainer with some Microsoft certifications, and you can see my contacts on the screen. Feel free to get in touch. It will be a pleasure to stay in touch. This second link on my contacts is a newsletter, a link for a newsletter that I publish. So if you would like to follow the newsletter, it will be a pleasure as well. So it will be a pleasure to stay in touch. So what are we talking today? Why and what is Azure SQL Ledger? How Azure SQL Ledger works? Provisioning an Azure SQL Ledger database, types of tables in SQL Ledger database, Azure SQL Ledger system tables, demonstration, and we'll talk about the external storage related to Azure SQL Ledger. So, what's Azure SQL Ledger? Why and what's Azure SQL Ledger? So first, let's talk about why. Some solutions require a higher level of data integrity than usual. That's the point about what we are talking today. Sometimes you need to prove your data has not been tampered with. No one has changed your data. No one has modified your data. Blockchain is one technique used for that. Of course, you may have heard about blockchain, but blockchain is decentralized, and the decentralization of blockchain can be a huge overkill. It becomes very complex, can be very difficult to implement. And example of some needs for this. A gaming player's wallet, for example, the gaming wallet without the transactions for the players. In this situation, it's unacceptable that any of the previous records pass by any change of data. Pass tracking, an industry, a car factory, for example, can be tracking parts of a car, and in this way, identify if some of these parts need a recall, are in need of a recall, and what are the clients of the factory which are affected by a possible recall. Some companies are already using third-party solutions to achieve this level of security that we are talking about as workarounds for that. And the point is that now these third-party solutions are not needed anymore. Okay, but what level of security are we talking about? We're talking about security, but what kind of security? Security that will prevent a hacker to break into our system? For what we are talking about, this is considered something basic. We're not talking about this. We're not focusing on a hacker trying to break into our system. We are considering that the system is protected against this. The kind of security that we are talking about is a different kind of security. It's the kind of security to protect the system against a CEO demanding that an employee change the data. For example, demanding an employee to change a record, to falsify a record inside the database. And we're talking about a level of security that not even if the CEO requests this, demands this, it's impossible to be done without leaving an audit trail. This is the level of security that we are talking about. So no one inside the company can falsify the data, can create false information, can modify the data without leaving an audit trail that will prove that this happened, that this problem happened. And once we achieve this level of security, the data in the company database can be used as proof in process moved by customers. For example, imagine if someone, John, has a problem with his car, and he discovers that the company, the car factory, made a recall of some parts, some cars, and some parts of the cars. And he decided to open a process to sue the company, complaining that his car should have been included in the process, should have received a recall. And what happens? The company needs to prove that John's car should not be included in the recall. The parts in the John's car were not affected by the recall problem. The company needs to prove that, to prove this information. Okay, the company can provide the data from its own database, but then we get to the question, what if someone inside the company changed the data on the company database to prevent the company to lose the process? That's where this level of security we're talking about comes into place. We're talking about a level of security that will be high enough for the data in the company database to be used as a proof that of an information, and that information was not changed or falsified by any employee in the company. By any employee in the company. That's the security we're talking about. Okay, and how is this possible? How does it work? So, each transaction that happens in the database is recorded as a history. So, a history of the transactions is kept in the database. Then, digest blocks are created for the transactions. Each transaction generates a digest block, a digest hash of that transaction, of that state of the database at that moment. Then the digest blocks are saved externally to the database. So we need an external storage where these digest blocks will be saved. And we need to ensure this external storage is immutable. There are some methods to ensure that these external storage are immutable. The digest can be used for integrity verification. So after the system is running, we have each transaction recorded as a history, the digest blocks being created, the digest being created inside the database and on the external storage. Then at any moment, the digest can be verified. The digest can be verified between the database and the external storage. And verifying the digest between the database and the external storage will tell immediately if any data was modified, if any data was falsified outside the scope of a regular transaction. And so let's go into more details about how Azure SQL Ledger works. The transactions are recorded in a system table. SQL Ledger uses a system table to record the transactions. The digest blocks are created for each transaction. The digest blocks are asynchronously transferred to an external storage. The transfer is asynchronous, so it doesn't affect the workload of the database. Verifications can be triggered regularly, so we can trigger a verification of the data once a day, once a week. So we can trigger regularly the verification of the database. Then, how do we create a database like this? How we provision an Azure SQL Ledger database? When we are provisioning an Azure SQL database, we have this configuration: Ledger, Preview. I haven't updated this image before, but the point is that during the build conference, which happened a few weeks ago, the Ledger, Azure SQL Ledger, went GA. So Ledger is generally available in Azure SQL. And here, during the provisioning of an Azure SQL database, we can configure the Azure SQL database to use Ledger. So we enable our filter tables in this database to use Ledger. This cannot be changed after the provisioning. This configuration is set during provisioning and cannot be changed after provisioning. And then we enable an external storage for the digest. We enable here an external storage for the digest. The external storage can be a regular Azure storage. There is a special requirement for the Azure storage to work. There is a special policy that we need to apply in this Azure policy, in this Azure storage, for it to work well with Ledger. Otherwise, the system would still have some flaws, would still be possible to falsify some data in some situations. So to prevent this possibility, there are some policies that we would need to apply in the Azure storage. Or the other option is another solution. It's important to not mix the solutions. There are two kinds of solutions. One solution is the solution called SQL Ledger, which it can be used in an Azure SQL database or SQL Server 2022. A different solution is the Azure Confidential Ledger. Azure Confidential Ledger is a different solution intended exactly to work as an external immutable storage for this kind of information, such as a digest that will prove that the data was not tampered with. Okay, so we make this provision. Then we'll create the tables inside our database. There are two kinds of tables that we create in a database enabled for SQL Ledger. Two kinds of tables. There is the updated ledger table. This is one of the kinds of table. An updatable ledger table, as the name says, it supports update. So we can update the data inside this table. It supports update, but keeps a history of all operations, including the update operation. All operations will be kept in a history. The technology used by Ledger is based on temporal tables. So Ledger is built over the temporal tables, but with some additional features. A view is used to retrieve information about the operations. If you would like to see the history of what happened with the data, we can use a view to retrieve this history about the operation, what happened on each operation inside the ledger table. So here we can see an updatable ledger table, how it works. So what exactly is this? Here we are seeing the user or an application. And here we are seeing the SQL database and what is inside the SQL database. And one ledger table. This ledger table is an updatable ledger table. This updatable ledger table, as the name says, can receive updates, can receive new records or update on older records. So the user will be working with this updatable ledger table. This updatable ledger table works in a similar way as temporal tables. So there is also a history table. The updatable ledger table keeps a history of the records. So if the user updates a record, the old version of the record is kept inside the history table. And we have a view called ledger view that joins the data from the updatable ledger table and the history table and show to us all the information, all the transactions that happen in this table, all change of data that happen in this table. So if anyone try to falsify any kind of information for the company to win some kind of process, we would see an audit trail. So an auditor would be able to see that the information was changed when it was changed, when that information was changed. So, and would be able to see the original information in the table. And in system tables, the digests are created. Each transaction, each activity over this table creates a digest, and the digests are linked to each other. Each digest is used to create the next one, and the next one, and the next one, so the digests are linked to each other in a similar method as it's done in a blockchain environment, in a similar way as it works in a blockchain. These digests are asynchronously saved in an external storage. So here we have an Azure storage account or confidential ledger saving these digests. So if anyone inside the company tries to manipulate this data, the external digest can be compared to the digest inside the database, and an attempt to falsify data would be identified. In Azure SQL, this would be very difficult. How to falsify some data inside Azure SQL? But it would be possible in a non-premise SQL Server or a SQL Server running in a virtual machine. It would be possible But the verification process made with the external storage can identify that the information was not modified, was not falsified. The other type of ledger table is the append-only ledger table. The append-only ledger table only accepts new records. An append-only ledger table can't accept updates, doesn't accept updates, only accept new records. So no update is accepted on this kind of table. If no update is accepted, there is no need for a history table. Why to keep a history table? All the data inserted in the table is the data which was inserted there. There is no update. And the view in this case is less useful because it will show only the records that we have in the append-only table. All them were inserted, no update operation happened. The view exists, but is not so useful as it is for the updatable ledger table. We will see this in an example. The system tables for ledgers, system tables. We have sys database ledger transactions. This system table stores the transactions which happen inside the database. And then we have the blocks. Each transaction generates blocks which contains the digests for the transactions. Then we have the system ledger table history and system sysledger table history and sysledger column history. What is these tables hold? These tables hold schema information about the tables, the columns. The action to create the table is registered in the sysledger table history. The action to create a column or to rename a column is kept in the sysledger column history. So a possible attempt to falsify data would be to create a new table with the same name, or create a new column, delete a column and create a new column with the same name. Everything is registered. No attempt to falsify the data would be untracked in the system. Everything would be tracked. And sys database ledger digest locations hold the information about the external storage. Where is located the external ledger storage to make verifications of the ledger transactions and verify that everything is okay with the ledger transactions. Let's do a demonstration about this. So I'm connected to a server, an Azure SQL server. Let me just open my tool, choose Zoom. And then show that I'm connected to my Azure SQL server. And I have here a database called Ledger Malta. So this database called Ledger Malta is the database enabled for Ledger. Let me open a script, a demonstration script, to show how this works. So I'll create a schema, path tracking. And then I'll create a table call paths inside this schema. So I have an ID, serial number, manufacturing date, batch ID, car ID. I'm simulating the example that I told about a car factory. Then we use system versioning on, ledger on. We can provide a name for the ledger view, parts ledger view. Since I'm not specifying in opposite, this will be an updated ledger table. So I create a table as well. The table is created. Let's take a look inside the database. So here inside the database, the table path tracking parts was created and a history table was created for this table as well. The history table is ledger history for and a number. What is this number? The object name of the main table. The object ID of the main table is used to build the name of the history table. Then I have the views, and together the views we have the parts ledger view. Part ledger view, which is the name that is specified here. I'm not going so much in details in relation to the create table process because the create table process can be completely customized. We can customize the name of everything, for example. And some hidden columns were created. Here we can see some hidden columns created inside the ledger table. So ledger start transaction ID, ledger end transaction ID, ledger start sequence number, ledger end sequence number. What these fields mean? These fields means the start and end of existence of a history record. When that record started to exist inside the database, and when that record stopped existing inside the database. When it started and when it stopped. And for the start and the stop, for each one, the start and the stop, we have an ID of the transaction responsible to put that record as the active record, and a sequence number inside the transaction, a sequence number of the activity inside the transaction. We have both for the start and the end of the record. We'll see these working in some moments. Then I can make a query on the SQL Database Ledger transactions. A transaction was already executed. A ledger transaction was already executed and generate a hash. So transaction ID 1327, block ID 0. Okay, and this generated a hash. I can check the ledger blocks, database ledger blocks, and you see the block transaction root hash, the hash of this transaction generated by the ledger. So block ID is 0. The transaction is linked to the block ID 0. That's everything that we have inside this database at the moment. We can take a look on the storage. I have, it's better if I use the Azure Storage Explorer. Let me open the Azure Storage Explorer. Okay. So I have here the Azure Storage Explorer, and I have a storage called Ledger Malta. I'm using this storage called Ledger Malta to store the digests. So let's take a look on the blob containers. So SQL Ledger digests for this server, central data. Ledger Malta, the name of the database. And I have a folder with date and time of the operation that started to save data here. And I have a first file called one. I can download this file and take a look on it. On Notepad. So we see the file use the JSON format, and the file contains the information about the transaction and the hash of the transaction. Contain the information about the transaction and the hash of the transaction. Okay. Now let's check also the history. The history table for this my ledger table, and the history is empty. Why the history is empty? Well, I haven't inserted or updated any record, so it's absolutely normal that the history is empty and the view is also empty. There is no record. But the table was created. There was one transaction. Yes. And I can see the transaction if I use the SQL Ledger table history. That first transaction is located in the SQL Ledger table history. Here I can see the transaction, which was the creation of a table creation, transaction ID 1327. 13.7, the creation of the table. If I take a look on column history, then I can see the creation of each column inside the table. Everything is hashed as a history information. The column ID and each operation got a sequence number, a transaction sequence number. The sequence number 0, sorry, that's not to create a new one. The sequence number 0 was given to the creation of the table itself. The creation of all the other columns got a higher sequence number. So we have a higher sequence number for the creation of the other column. Okay. Then, let me create multiple transactions in a single execution, but I'm executing them together, but I'm breaking down with a goal in the middle, so there'll be two different transactions, and they'll be inserting them inside the table. Inserting two records inside the table. Let's take a look on the table itself, the two records will be there. So I have my two records inserted here. Then I can see the history of ledger transactions. So two different transactions were created. But since I sent them very close to each other, they were inserted in a single block. The break of the blocks, if the transactions will get into a different block, or if the transactions will get in the same block, is defined by a period of time. The blocks are built in a 30 seconds period of time. The transactions during 30 seconds get inside the same block. So block ID 1, and then since the same block has more than a single transaction, a transaction ordinal was created. Transaction 0, transaction 1 inside the same block. So transaction 0 and transaction 1 inside the block. I can check the blocks and I'll see that I have the block 0 and block 1. Block 1 contains two transactions. I have 3 transactions but only 2 blocks. Block 1 contains 2 transactions. The history. Can you imagine how is the history at the moment? Let's execute. The history is empty. Why the history is empty? Because there is no past record, no old version of the records. The records were not updated. The history is intended to keep old versions of the record. If a record is updated or deleted, it will become history. But since this hasn't happened yet, I haven't updated or deleted any record, so the history is completely empty. I have no history. Then I can check the ledger view, parts ledger view. And the view tells me the operations which happen on ledger. So I can see here on this view the insert operations which happen on ledger and the transaction IDs of these insert operations and the ledger sequence numbers. In this case, this ledger sequence numbers is not the same as the transaction sequence number in the block. This ledger sequence number is intended to show if more than a single operation is inside the same transaction. So here on the view, we have a ledger sequence number on the view, while on the blocks, on the transactions, we have the transaction ordinal in relation to the block. We have the transaction ordinal in relation to the block, and we have the ledger sequence number in relation to the transaction. Thank you, Thomas. Thank you for attending. See you. Bye. And then let's make an update on our data. Let me update the table parts, set car ID equal to where car ID equal where ID equals to. So let me double check the content of the table. So the car ID in the table is completely empty. But I have the ID, which is 1 and 2, And then let's update and set the car ID equal to where ID is equal to. Execute, and let's check the table. So now I made an update on the record. This record had the car ID null, and now this record has the car ID 2. So the record changed. What happens with the history table now? On the history table, we can find the old version of the record. The old version of the record with ID 2, had the car ID null. This is a version which is not current anymore. So it's telling us as well on which operation and sequence number this record became current in the table. On the transaction 1366, sequence number 0, this record became current in the table. But on transaction 1387, sequence number 1, this record became an old version in the table. Sequence number 1, not sequence number 0. There is a reason for that. There is a reason for that sequence number. We can make a select on the view, and it's better if we order the content of the view by transaction ID and sequence number. And now I can see the operations which happen in this table. So, first we had two inserts. We insert the record 1 and we insert the record 2. And we have here the date of both records and the transaction ID when these records were inserted inside the table. Then we made an update. We made an update on the table. The update appears as an insert and delete. So the old version of the record was deleted and the new version of the record was inserted. So the update appears as an insert and delete. So we can see the old version is the version which had null, was deleted. On the transaction 1387, sequence number 1. Sequence number 1 because the sequence number 0 is the insert of the new record. The new record where the car ID is 2. So the update generated two operations inside the ledger table. Two operations were generated inside the ledger table. And we assume two operations were generated inside the same transaction. We can check the transactions. We got a new transaction, 1387, and this new transaction got the block ID 2. So the block ID 2 got this transaction 1387, which is the update. Then let me check the block. So we have now another block. So we already had the block 0. Then we had the block 1. The insert of the records were block 1, and the update of the record became block 2. The update of the record became block 2. I have the transactions root hash, and I have a previous block hash. But this is a bit difficult to visualize. The relation between them is a bit difficult to visualize on the system table. This is database ledger blocks. But if I open the file here from the storage, I can visualize better the sequence of the data. So We have the relation of previous hash. The previous hash is displayed in the table. So it's saying that the previous hash for the block ID 1 starts with 0xfc. 0xfc. Well, the hash of the block 0 is 0xfc0. So this is the hash of the block 0, the hash of the previous block. Then the second block, 0BA7. And if I check the first block, this is 0BA7. So the blocks build a chain, build a sequence chain. And this makes the process faster. The previous block is used to build the next block, creating a chain of hashes, a chain of hash that will ensure the security of the data. Then let's see another example. Now I'll make a transaction, one single transaction with multiple steps, in this case multiple updates. I'll be updating both records, record 1 and 2, to car ID 3. Both records will have the car ID 3. Okay, so I'm executing this in a single transaction. Let's check the content of the table, of course. We just updated the table, so both records have car ID 3. Yes, both records have car ID 3. But now if I check the history, I can see the old records are inside the history. And the record with ID 2 is already appearing twice in the history because I made 2 updates inside this record or over this record with ID 2. I made 2 updates over this record, so it's already appearing twice in this history table. Okay. Then I can check the view to see the sequence of operations. And we can see that we have many operations which happen inside the transaction 1392 because I created 2 updates inside the same transaction. Inside the same transaction, I made 2 updates. And each update becomes an insert and a delete. Each update becomes an insert and a delete. So we have 4 operations inside the same transaction. And we have a sequence number 0 to 3, a sequence number built on this transaction. The view translates for us the operations which happen over the tables. The view uses the information from the main table and the history table to translate the information for us. So we can check the ledger transactions. And checking the ledger transactions, we can see this last transaction here generated a new block, block 3. And we can check ledger blocks, block 3. We already checked the previous block hash on the storage. We are seeing a chain of digests being built on the storage. And this chain of the digest is also inside the system tables. The database has this information and the storage has this information as well. Okay. Now let's try a delete. I can make a delete over this table. I will delete the record with the ID 2. So I can delete this record with ID 2. This will generate a new transaction, the transaction 1400 as a delete, and they'll generate a new insert. Let's insert a new record. I generated an insert, which also generated a new transaction, 1403. Okay, let's see this sequence of activities. At the end, we see a delete and an insert, but then following the information, we can tell these are isolated information. They happen in different transactions. So one was a delete of one record and the other was an insert of a different record. And we can follow the operations that happen on this table using the ledgers view. Then, let's try an append-only table. Create schema transactions. Now I'll make the example with the wallet transactions for gaming users, for example. User ID, the operation, which will be credit or debit. A timestamp for the operation will be the get date and the amount of the transaction. Then ledger on will be enabling ledger and append only on. So this table will be append only. Let me execute. Okay. Then I refresh and I can see the wallets table. Since the table is append only, a ledger append only table doesn't create the history table. There is no history. Nothing will be deleted from this table. Nothing will be updated on this table. There are no old versions of the record. There is no history for a ledger append-only table. The columns as well, they have only a start. There is no end column because once a record is inserted in this table, it will not leave the table anymore. It will be there. Once a record is inserted in the table, it will not leave the table anymore. But the view is created. The view is created to still give us a consistent method to see the operations happening inside this table. So, after creating the append-only table, we can see the table history. Table history, you'll see now the creation of a second table, the wallets table, and you'll see the transaction ID for the creation of each table. For each table, you see the transaction ID. Then, database ledger transactions, we have the transaction of the creation of the table here with a block ID 6. Let's insert many records inside this table. Insert many records inside this table. Okay. Then, okay, make a query on the view, and I'm seeing the sequence of insert. Each insert is a different transaction. Each insert I made on the table is a different transaction. But since I made all of them at once, I sent them all at once to the server, they were executed very closely to each other, all these inserts generated one single block, the block 7. So the block 7 contains a total of 9 transactions. 9 transactions were inserted inside block 7. I have one block, block 7, with these transactions. Then, this is just to make the example more visible. Once I created a wallets table, I can create a running total on the wallets table and see a running total by user ID, by each operation in the transactions table and by user ID. So I have a running total for user 1, how the balance of this user changed on each operation. I have a running total for the user 2, and I have a running total for the users 3. But we could make a running total. We don't need the ledger to make a running total. Yes, we don't need the ledger to make a running total. The problem is, do we trust the information? Do we trust this information here? Before ledger, we could not totally trust this information. How could we be sure that no one, no DBA, had falsified this data? We could not be sure about that. Anyone with a sysadmin access to the database, or even a lower access than sysadmin to the database, could have falsified some transaction. But with Ledger, we can identify that this hasn't happened. So we can trust some query results like this one, showing a running total of the transactions. If I make an update, I'm totally capable to identify that this update happened. In case I execute an update about of an operation, I'm totally capable to identify that this update happened. And when I would like to verify if something went wrong on my environment, I can use a store procedure called sysp verify database ledger from digest storage. I would like to use this store procedure for the verification. I need to get the digest location. So this process requires me to send to the store procedure the digest location. Where is my digest stored? Where are the hashes stored? So I recover the digest location from the SQL Databases Ledger digest locations and put the result in the digest location variable. Okay. Then I execute. So ledger verification succeed. So I fill the variable digest locations. I'm showing the value of the digest location. This is the first select showing the location of the digest on my storage. Then last verified block, block ID 7 was the last one verified, and the ledger ensures that everything up to the last verified block is correct because it's matching the digest. Then ledger verification succeed. So the verification of the data was succeeded. Okay. Uh, there are some important details in relation to the external storage because, for example, here, my external storage is in a storage account. How can I be sure I can't manipulate this storage account? There is a method for that. There is a trick not many people know about is storage account. Ledger Malta. Let me get the storage account, Ledger Malta, get the container, and inside this container, which contains the digests, we can create, let me locate an access policy, and we can define an immutable blob storage policy. Immutable blob storage. If we define an immutable blob storage policy, not even the Microsoft employees are capable to change the data in this blob storage. So there are two kinds of immutable blob storage policy: legal hold or time-based retention. The point is that the legal hold will completely block the content of this blob storage. I would not be able to change the files. But the ledger needs to be able to continue saving digest inside this file. How the ledger can be able to save digest inside the file and at the same point ensure that no one, not even ledger, is capable to change what's behind on this file. Like the file type, the blob type is an append blob. An append blob inside the storage account only accepts new records, only accepts appending information, doesn't accept changing old information. And by creating an immutable storage policy with a time-based retention, I can allow only append blobs to receive new writes. Append blobs can receive new writes to the end of the blob. And then I can specify a time period in days, 365. But what happens when this period expires, when this time-based retention policy expires? The data continues immutable. Continues immutable. If the time-based retention is expired and is not renewed, what will happen is that the data can be deleted. Files can be deleted. All the files can be deleted, but the data can be changed. Can be deleted, but not changed. But anyway, this is something you could take care by renewing this retention policy, automating the renewal of this retention policy in the blob storage. This is something you can take care about. And that's what is here about external storage. We can use the Azure Storage Account or Azure Confidential Ledger. If we use the Azure Storage Account, there are some requirements. There is a property called hierarchical namespace on the Azure Storage Account. This property needs to be disabled. Ledger is not compatible with this property. But in fact, it's exactly this is exactly the reason. The immutability policy, this immutability policy that I just illustrated to you, only works when the hierarchical namespace is disabled. But if you create the storage account for Ledger during the provisioning process of Azure SQL, the storage account is already created correctly. It uses an append blob. The content type of the append blob is application octet string. Just to make things more complex, the content type is application octet string. Of course, I tried to tamper with this data. I tried to download this data, change and upload a new version of the file. But if I try to edit in a notepad, for example, the content type of the data changed. A ledger doesn't accept anymore, and it doesn't pass the verifications anymore. So an attempt to tamper the data is noticeable. It's possible to tamper the data. It's possible to tamper the data. There are methods to keep the same content type. That's why this will only work well if you create the immutability policy in the container. You need to create the immutability policy in the container. So it is extremely recommended. Apply a immutability property to the container. Here, access policies. You create a mutable blob storage policy, and it needs to be time-based retention to allow append blobs. So it will allow append blobs. And the other option is to use Azure Confidential Ledger. It's an Azure service to store immutable data. Use multiple blockchain nodes on the backend. So it's also technology based on blockchain. It is or it was in preview. I'm not sure if Confidential Ledger went GA on the build as well. Ledger went GA during the build. I'm not sure about Confidential Ledger anymore. So we can see here how the Confidential Ledger is used to store informations. Your application can store information in Azure Confidential Ledger, and Azure Confidential Ledger use a secure enclave-based ledger backend with multiple replicas to ensure the information cannot be tampered with. Reference SQL Ledger documentation, some articles about SQL Ledger, a SQL Ledger white paper, and Azure Confidential Ledger documentation. These are not regular reference. These articles goes very deep on the method of work of SQL Ledger. They go very deep on this method of work, especially the white paper. The white paper provides you a lot of details about Azure SQL Ledger. I will soon be publishing many articles about SQL Ledger based on the content I discovered on the white paper. The white paper about SQL Ledger contains a lot of details, the internals about how SQL Ledger works. So here is me again, my contacts. Thank you very much for attending this session. I hope you like it. I hope this session inspired you to use this technology in some of your environments so you can have a more trustworthy set of data in your environment without the need to rely on third-party softwares. You can have this in SQL Server and Azure SQL as well. Anyone has any question? Anyone would like to ask anything? No questions? So, thank you very much for attending this session, and we'll see you soon again in a new meetup. Thank you very much for attending.